In the dynamic world of Elasticsearch, the quest for optimal performance is paramount. How can we unlock the full potential of query optimization in this distributed search environment? It's a journey that intertwines the threads of performance, relevance, and efficiency. Picture this: each query a puzzle piece, fitting seamlessly into the larger picture of a well-oiled search engine. Through strategic indexing, intelligent caching, and smart shard allocation, we aim to strike the perfect balance between speed and accuracy. As we delve deeper into the intricacies of Elasticsearch optimization, we unearth a world where every millisecond counts and every tweak resonates across the system. Join us as we unravel the mysteries of query optimization and pave the way for a smoother, more responsive search experience. In this realm of Elasticsearch, mastery is not just a goal, it's a necessity. As you embark on your Elasticsearch query journey, the pivotal first step is query parsing. Here, your query DSL is transformed into an efficient internal representation for execution across distributed nodes. The query parser validates syntax, identifies query types, and maps out an execution plan. Moving into the planning phase, decisions are made on which indices and shards to target, the balance between filters and scored queries, and the potential reuse of cached results. This meticulous orchestration ensures minimal computational overhead and network traffic by interacting solely with pertinent data. In essence, meticulous query parsing and planning set the stage for streamlined and effective Elasticsearch queries. Ever wonder how query execution actually works behind the scenes? It all starts with parsing the JSON and validating the query DSL structure. Next, a plan is meticulously built to determine the execution strategy and shard targeting. Then, it's time to execute, running queries across shards in parallel for optimal efficiency. Once the results are in, they are merged, aggregated, and ranked to provide a comprehensive response. Understanding this workflow is key to diagnosing slow queries and enhancing search performance. In the complex world of query execution, every step plays a vital role in delivering accurate and efficient results. Proper index configuration is the cornerstone of Elasticsearch performance. How you set up your indices, shards, replicas, and refresh intervals directly impacts speed, scalability, and resilience. Inefficient configuration can slow down even the best queries, while strategic setup can significantly boost performance. Think of index configuration as the engine powering your Elasticsearch system. Just as a well-tuned engine drives a car smoothly and efficiently, proper index configuration propels your Elasticsearch queries to peak performance. In the realm of Elasticsearch's distributed architecture lies the crucial concept of shards. These shards, the elemental units of data distribution, play a pivotal role in optimizing efficiency. Primary shards divide each index, while replicas ensure redundancy. The art lies in shard count optimization. Too few hinder parallelism, while too many bring about unnecessary overhead. To strike the right balance, begin with one shard for every 20 to 50 gigabytes of data. Vigilantly monitor cluster performance and adjust as your dataset expands. Remember, altering primary shard count post-index creation necessitates a full reindexing process. Efficient data distribution hinges on this delicate shard dance. Ever wonder how replicas and refresh intervals enhance your system's performance? Replica shards are like loyal backup singers, boosting fault tolerance and read throughput. Starting with one replica per primary shard, you can horizontally scale replicas to handle more queries without slowing down writes. Meanwhile, the refresh interval dictates when new documents become searchable, with the default set at 1 second. Adjusting this interval can reduce indexing workload but may delay data visibility. During bulk indexing, a temporary setting of -1 buys time for loading before restoring visibility. Remember, balancing replicas and refresh intervals optimizes your system for both speed and reliability. Caching mechanisms in Elasticsearch, a powerhouse for performance optimization. By storing frequently accessed data in memory, Elasticsearch slashes computation time for repeated searches. Let's dive into how and when caching works to supercharge your query efficiency. Picture this: your queries running at lightning speed, thanks to Elasticsearch's robust caching system. Master caching to turbocharge your search performance. Ever wondered about the difference between query cache and filter cache in your Elasticsearch setup? The query cache stores complete query results at the shard level, perfect for repetitive filters on stable data, with LRU eviction to manage memory efficiently. On the other hand, the request cache caches aggregation results and hit counts for searches with size equals 0, ideal for dashboards and analytics. Remember to monitor hit rates and cache sizes for optimal performance. So, whether you're optimizing for repeated filters or crafting dynamic dashboards, understanding the nuances of these caches can elevate your Elasticsearch experience. Are you making the most of your cache? By utilizing filter context and wrapping non-scoring clauses in a bool query, you can boost efficiency and avoid unnecessary computations. Extend cache validity by refreshing less frequently, minimizing redundant calculations. Keep an eye on your hit rates to identify queries that may need restructuring. Remember, optimizing cache usage can streamline operations and enhance performance in the long run. In Elasticsearch, understanding the distinction between filter and query context is crucial. Filter context focuses on binary conditions like date ranges or categories, swiftly checking for matches without scoring. On the other hand, query context involves calculating relevance scores for each document, essential for ranked search results but computationally intensive. By choosing between these contexts, you directly impact performance and relevance scoring in Elasticsearch. Remember, filters are fast, cacheable, and perfect for yes/no conditions. So, when optimizing your Elasticsearch queries, consider whether filter or query context best suits your needs. In search queries, choosing between query and filter contexts can make a big impact on results. Query context is ideal for full-text searches with relevance ranking, fuzzy matching, boosting specific fields, and searches where order matters. Think match, multi-match, or match_phrase. On the other hand, filter context suits exact matches, date or numeric boundaries, Boolean logic, and binary yes/no conditions. Consider using the filter clause in bool queries for this. To maximize results, combine both contexts using bool queries, use must or should for scoring and filter for non-scored conditions. Make the most of your search queries by understanding when to leverage each context effectively. Ever wondered how Elasticsearch efficiently scales clusters to handle vast amounts of data and queries? In Chapter 5, shard allocation and routing take center stage. Through strategic shard distribution and query routing, Elasticsearch optimizes data distribution across nodes. Avoiding hotspots and uneven loads is crucial for peak performance in large, high-traffic environments. Think of shards as puzzle pieces meticulously placed to ensure seamless operations. Let's delve into the intricate web of shard allocation and routing, where precision is key to cluster scalability. Remember, a well-balanced shard distribution is the backbone of a high-performing Elasticsearch cluster. Ever wondered how shard routing actually works behind the scenes? Let's dive in. Each document gets assigned to a shard based on a hash of its ID, ensuring efficient distribution. But did you know that custom routing keys can group related documents together? When a query comes in, the coordinating node springs into action, sending it to the relevant shards, merging responses, and presenting a neatly sorted result. Elasticsearch's allocation strategy intelligently balances shards across nodes, taking into account disk space, heap usage, and shard count. By utilizing allocation filtering, you can fine-tune placement for specific needs, like organizing hot/warm architectures for time series data. In a nutshell, shard routing streamlines operations and optimizes data distribution for enhanced performance. Ever wondered how to optimize shard allocation for faster queries? By utilizing custom routing parameters, you can ensure related documents land on the same shard, slashing cross-shard joins and boosting query speeds. Remember, keep your shard sizes between 20 to 50 GB to avoid sluggish recovery and rebalancing. Additionally, employing the preference parameter in search requests can direct queries to specific nodes or shards, enhancing cache hit rates. Tailoring your shard allocation strategy can significantly streamline your system's performance. Ever wondered how Elasticsearch handles complex data summarization in real time? Chapter 6 dives into aggregations and performance, showcasing the framework's analytical prowess. While aggregations offer invaluable insights, they can strain resources with large datasets or high cardinality fields. To optimize performance, grasp the memory and CPU costs, utilize caching strategically, and streamline queries to reduce the document workload pre-aggregation. Harness the power of aggregations wisely to unlock actionable metrics and accelerate data processing efficiency. Takeaway: mastering Elasticsearch's aggregations is key to unlocking real-time analytics while optimizing resource utilization. Are you looking to supercharge your aggregation performance? Here are some key tips to optimize your data processing efficiency. Filter before aggregating. Trim down your dataset using filters before crunching numbers. Smaller datasets mean quicker aggregations and less memory usage. Limit cardinality. Watch out for high cardinality fields, they can hog memory. Try using execution_hint or sample data to lighten the load. And think about composite aggregations for smoother pagination. Use doc values. Make sure your aggregation fields have doc values enabled for a speed boost. Doc values streamline the process, outperforming field data in memory. Avoid nested aggregations. Deep nesting equals heavy memory usage. Simplify your data models where you can or break complex aggregations into simpler queries. Remember, optimizing aggregation performance is all about smart strategies. So, filter wisely, watch those cardinalities, embrace doc values, and steer clear of nesting overload. Ever wonder how search engines decide which results to show first? In Chapter 7, we delve into relevance scoring, TF-IDF and BM25. These scoring methods determine the order of search results by assessing how well documents align with the search query. While Elasticsearch initially relied on TF-IDF, it now favors BM25 as the default algorithm. Understanding these models allows you to enhance result quality and provide clear explanations for result rankings. So, how does your search engine decide what's most relevant to you? Let's uncover the magic behind the scenes. Ever wondered about the inner workings of document scoring in search engines? TF-IDF and BM25 are two key algorithms in this realm. TF-IDF, the classic approach, assigns scores based on term frequency and inverse document frequency. While simple, it may skew results for longer documents by emphasizing term repetition. In contrast, BM25, the modern default, introduces saturation to prevent diminishing returns from excessive term occurrences, along with document length normalization. Parameters such as K1 and B can be fine-tuned per index to refine ranking behavior. Since Elasticsearch 5.0, BM25 has been the default choice, offering robust performance for most scenarios. Remember, tweaking K1 and B can tailor the algorithm to suit specific requirements. In a nutshell, understanding the nuances between TF-IDF and BM25 is crucial for optimizing search relevance effectively. Ever wondered how to diagnose slow queries efficiently? Chapter 8 introduces profiling and benchmarking, where the Profile API becomes your go-to tool. It breaks down query components' time consumption at the shard, segment, and query clause levels. Dive into the details by enabling profiling with a simple addition to your search request: profile, true. From query execution to fetch phases, the response provides precise timing breakdowns, empowering you to pinpoint time-consuming areas. Uncover bottlenecks and validate optimization efforts with this essential visibility. Master your queries with the Profile API and take control of your optimization journey. Are your monitoring metrics hitting the mark? Keep an eye on your cache hit rate, aiming for 95% efficiency. Dive into query latency, ensuring responses stay swift under 50 milliseconds. Watch that heap usage doesn't max out at 70% to avoid performance hiccups. Optimize with filters, adjust refresh intervals, and fine-tune JVM settings for peak performance. Remember, profiling and monitoring are ongoing journeys toward optimal efficiency. Stay sharp, stay agile, and keep tuning for success.